Okay, so now we're going to talk about the characteristics of rational functions. The first thing we should do, though, is define what a rational function is. So a rational function is the ratio, thus rational, right, ratio, of two polynomial functions. So r of x would equal p of x over q of x, where q of x and p of x are indeed polynomials. Now, what this might look like is you could have r of x, let's get on the right tool here, r of x equals, let's say, x squared plus 3x plus 2 over x squared minus, 6x plus 5. Those are both quadratics, polynomials, so that would count as a rational function. Now, oftentimes, it is very useful to have these in factored form when you're finding the characteristics. So brushing up on factoring might not be a bad idea. So being able to factor things is going to be kind of key when it comes down to this, because being able to find the roots and of the numerator and denominator is going to be kind of important. Okay, so these are the characteristics that you're going to be able to figure out once you've viewed this video. The zeros, something called the vertical asymptotes. Those are vertical lines of the form y equals that the graph, x equals that the graph might approach but not cross. Horizontal asymptotes are long-term behaviors in the graph, and they are horizontal lines that the graph approaches. Oblique or slant asymptotes would be what appear to be, if you zoomed way out, linear equations that this graph is approaching. You'll see what I'm talking about when we get there. Removable discontinuities. These things do have discontinuities. Those are the asymptotes, particularly the vertical asymptotes. Removable discontinuities that appear as holes in the graph, and we'll talk about that behavior when we get there. And then the end behavior, which we have talked about before. This is the whole as x tends towards positive or negative infinity, y tends towards what, right? Same thing applies. There are some shortcuts too. And then continuity is more about where is the graph discontinuous. So it's more like more talking about the discussion of the continuity of the graph. So let's get started. So let's say we're looking for these zeros. Now that would be when the numerator is equal to 0. So we're looking for the zeros, aka when the y value is equal to 0, so when this whole thing equals 0. Now if I were to multiply both sides by, in this case, the denominator, x minus 2 times x plus 5, right, and I do that to both sides, it would cancel out here, and 0 times anything is 0. So really what I'm looking for are when does the numerator, top right, equal 0. So in this case, we'd say that the zeros are 1 and negative 3, those two x values. That'd be it. The vertical asymptotes are when the denominator is equal to 0, because as we know, dividing by 0, so something divided by 0 equals not good. And these end up displaying what is called asymptotic behavior. Now if we think about y equals 1 over x, that's one of our simpler rational functions. The denominator there is equal to 0 at 0, which is why we end up with this asymptotic behavior of that graph, such that the line x equals 0 would be a vertical asymptote. Now in a more complicated graph like this one, we're looking for when we're dividing by 0. And so we would say that the vertical asymptotes, often abbreviated VA, would be when x equals, well, when does the denominator equal to 0? Well, when x is positive 2 and when x is equal to negative 5. Now the reason I'm writing these out as separate equations is because these are two vertical lines, like this, right, where this graph is approaching but not crossing. So to sum up, when the denominator is equal to 0, factored form is very handy. Horizontal asymptotes, I've got a couple of cases here, but in general what you're looking for is the long-term behavior. Now, looking at this graph, this would appear to be, well, if you distributed it. Now, what we're going to do is we're going to take the limit as x tends towards positive or negative infinity and see what happens. Now, when we're doing this, we're basically looking at, okay, for very large values, what's going on? So here's my argument. If I were to actually distribute this, I would get x squared plus 2x minus 3 over x squared plus 3x minus 10, right? Now, the idea is I'm going to be plugging infinity in. So over the long haul, what's happening? That is, over here towards positive infinity, what's going on? And over here towards negative infinity, what's going on? Now, if this looks like the end behavior, it is. It just so happens, though, that something interesting does occur when we do this. Now, if I were to plug infinity in here, I'd have like infinity squared. So if I actually plug that in, I have infinity squared plus 2 times infinity minus 3 over infinity squared plus 3 times infinity minus 10. Now here's the deal. Infinity is an infinite number, as in it's large, and it gets larger, has a high magnitude, right? The farther along we go. Now I've just plugged positive infinity in here, and it turns out in this case it won't matter. But the idea is if I take infinity, or infinity squared for that matter, and I subtract 3, that 3 is not going to meaningfully change the value, so we can ignore it. The same is true for the minus 10. We can just ignore it. Compared to infinity, pales in comparison. Now here's where the fun really begins. Infinity squared is infinity infinities. If I have an infinite number of infinities, how does a mere 2 infinities compare? The answer, it doesn't. Has no meaningful effect. Same on the bottom. So the basic gist of this is when I'm looking for horizontal asymptotes or end behavior, I'm just going to focus on the highest power of the numerator and the denominator, which in this case happen to be x squared and x squared. And then I can plug in infinity and simplify. Now, infinity squared over infinity squared, those are comparable. What does that tend towards? That tends towards 1. What is something divided by itself? So in this case, we would say that the horizontal asymptote, H-A, would be y equals 1. And if you graph this out, in the long haul, this is going to head towards the horizontal line 1. Now, for horizontal asymptotes, if they exist, the graph could be doing other fun stuff here. Like we know it has these 2 vertical asymptotes, so we know that it's going to cross that 1 short term, but long term it's going to head towards 1. So using this rule, if I'm looking at this, all I need to figure out the horizontal asymptotes is to take a look, and if I've got this over this, right, that is, these are both squared. So when I do 3 times infinity squared over 5 times infinity squared, the infinity squares cancel out, so we'd say that the horizontal asymptote is 3/5, and that's it. Or if I'm looking at this, highest power in the numerator is x squared, highest power in the denominator is x cubed, so I can focus on those. What is infinity squared over infinity cubed? Well, 2 of the infinities cancel out, so I get 1 over infinity. What is 1 divided by infinity? What is 1 cut into an infinite number of pieces? Well, each piece is incredibly small, so small that we'd call it 0. So we'd say that the horizontal asymptote would be y equal to 0. So in general, if the degree of the numerator and denominator is the same, there is going to be some sort of horizontal asymptote, and that's going to have to do with the coefficients, that is the numbers in front of the highest powers. If the degree of the denominator is larger than the numerator, like in this case, then we know it's going to tend towards 0. So if you had something like x squared plus 4x plus 7 over x to the 5th plus 2x plus 5, then you can pretty much tell right away that the horizontal asymptote is going to be 0. By the way, and I'll mention this again, if there is a horizontal asymptote, that is also the end behavior. Oblique or slant. Now in this case, you end up with a degree of 1 higher. Now, here's what happens. Now, I'm going to use synthetic division. Why? Because I can in this case. Sometimes you might have to resort to polynomial division. But if I were to pull out, remember that root is a -4, what happens? 2 times -4 is -8. So that's -5. -4 times -5 is 20. So does this go in evenly? No. But I do know that what's left is a 2x minus 5 in the end. So what happens is this, without the remainder, is what this graph tends towards long term. So if we think about this as 2 times infinity squared over infinity, right? I end up with 2 times infinity, which if you think about it is a line with a slope of 2. So what happens is, and sure enough, here's our specific line, this would be the oblique asymptote that we're heading towards, okay? Sometimes it's called a slant asymptote, but I typically use the term oblique. So if you look long term, if you zoom way out on this graph, right, zoom way out, it's going to look like y equals 2x. Is there going to be stuff going on here? Why, yes, there is. In fact, this has a vertical asymptote at x equals -4, so it's going to be doing something funny, probably like this and like this, right? But in reality, long term, it's going to look linear. And that's what we're talking about this. Now, the end behavior in this case, you look at the slope, and I know if it's a positive slope, as x goes up, y goes up. So then I can also use this to predict the end behavior, which in this case would be this. If it was a negative slope, then it would be the other way around, because it would be going down from left to right. Key thing, the degree of the numerator is exactly 1 higher, because if it's exactly 1 higher, when you divide it, you get a linear remainder, or a linear function as the dividend. All right, removable discontinuities. These graphs are discontinuous when the denominator is equal to 0. As a matter of fact, we would say that this has a vertical asymptote at x equals 2 and x equals -3. At the same time, we would say it has zeros at x equals 1 and x equals -3. Hopefully you notice that there's some duplication here. And under normal circumstances, we'd say, hey, wait, we can cancel those out. We can remove them, right? But here's the deal. Because we're removing them, right, is fine. That's the removable part. It can be factored out, canceled. But that also means that it's still undefined at that point. So if we were to look at this graph at x equals -3, something interesting happens. And it's very hard to see on a graphing calculator or in Desmos, but at -3, there's going to be a hole in the graph. In other words, it's going to keep going, but there's going to be a hole there because it cannot be at the same time a 0 or a vertical asymptote, right? And typically we use RD for this. Now, if something is a removable discontinuity, which x equals -3 is, then it cannot be a vertical asymptote and it cannot be a 0. So if you have this happen, just listed as removable discontinuity, not a vertical asymptote and not a 0, because they can't be both at the same time. In terms of the graph, it shows up as a hole. End behavior, self-explanatory, right? So when there's a horizontal asymptote, the end behaviors are the same. So if you have a horizontal asymptote of, let's say, y equals 1, then you know that the end behavior, EB, get it, is going to be x goes to positive or negative infinity, because we always start that way. Y goes to where? 1. If in this case we're looking at something like x to the 4th over x cubed, 2x cubed, we can still just isolate and take a look at the highest degree. And if we plug in infinity, we get a positive infinity to the 4th over 2 times infinity cubed, which is infinity over 2. So what this is doing is it's looking something like that, because I don't know if you've noticed, we could divide this out and it has an oblique asymptote, but we would say that in this case the end behavior for this particular graph, right, would be x goes to, notice how I'm always writing it out as this, y goes to, well, positive and negative, so as it goes to positive, y goes to positive, and x goes to negative, y goes to negative. Continuity. Basically, you take the vertical asymptotes and the removable discontinuities. So where is the graph discontinuous? It is discontinuous at x equals 2, because that was a vertical asymptote. And there's a removable discontinuity. If this looks familiar, it's one of the same equations, right? At x equals -3, because that had a factor in common. So we'd say it's discontinuous at these 2 points, these 2 x values. That's it. So you take the vertical asymptotes and the removable discontinuities, altogether they make up the points of discontinuity of the graph. And that's actually it for our whirlwind tour of rational functions and their characteristics.